This is going to be a little bit of a review from the last lesson. So today we are going to look at Hubble's Law. So if you could write this question of the day down. How does Hubble's Law help determine the distance to the most remote galaxies? Let's find out. Which color of light has the longest wavelength? Red. Which color has the shortest wavelength? Blue. And remember our good friend, the Doppler effect.
Imagine a fire engine. Its siren emits sound waves. As it rushes along the road, the crests of the sound waves in front of it are closer together than those behind it. Since the distance between the crests of sound waves determines pitch, the engine sounds higher as it approaches and deeper as it moves away. This is due to something called the Doppler effect, and it affects light waves emitted from moving sources too. Now shorter waves appear bluer, and longer waves appear redder. We can use this blue shift and red shift of light to study the motions of things in space.
Not just sound that does this, it's also light. So light will get smushed together, or it will get stretched out. So if something is coming towards us, those light waves are going to be smushed and it's going to be blue shifted. If it's going away from us, they're going to be stretched. It's going to be red shifted.
The only person in this conference.
It's going to be red shifted. And it's not the color of the object that changes. It's the spectral lines get shifted either towards the red end or the blue end. So if something is moving away from us, these spectral lines are going to be shifted towards the red end of the spectrum. If you know how much it's red shifted, you can figure out how fast it's moving away from us. So whatever percentage it is redshifted over, you multiply that by the speed of light, and that will be the percentage of the speed of light that that object is moving away from us. We would have done a lab in class. What we would have done is been in groups, and each group would have gotten a balloon. And you would have put dots on the balloon. You'd have blown it up a little bit, drew some galaxies on that balloon, and then you would have put more air into the balloon, and it would have inflated, and your job would have been to measure how far it was between the galaxies originally, and then remeasure after you put in like 2 more breaths, and then put 2 more breaths into the balloon, and it would have inflated more, and you measure how far away those galaxies are again. The idea is that as the balloon got bigger, those dots, those little galaxies that you drew on the balloon, would have been farther away from each other. That is actually happening in real life. That's happening to our universe. Our universe is expanding. Our universe is getting bigger. There is more space each and every second. So our universe is bigger today than it was yesterday. When you're listening to this Edpuzzle, you are living in a bigger universe than when I was making this Edpuzzle. Our universe is constantly getting bigger. And because of that, the galaxies that are in the universe are constantly, along with space, just moving apart. They're moving away from each other. When you measured the distances between the galaxies on your balloon, you would have noticed that if they started out farther away, that after you blew the balloon up, they were farther apart than the galaxies that started out closer together. So the galaxies that are farther away from the Milky Way are flying away from us faster than galaxies that are close to the Milky Way, because there's more space in between to expand. Hubble figured this out. He noticed that the farther away a galaxy is, the faster it is receding away from us. And he plotted this on a graph. So he put the distance, how far away is that galaxy, and the velocity that it was moving away. And it turns out this is a very well-defined relationship between how far away a galaxy is from us and how fast it is speeding away from us. How did Hubble find these distances to these faraway galaxies? He used Cepheid variable stars. He used supernovas. So he knew exactly how far away very distant galaxies were. He measured their redshift and realized that the farther away they were, the faster they were.
Currently the only person in this conference.
The farther away they were, the faster they were receding. The slope of this line is what is known as the Hubble constant, and it describes how much faster those distant galaxies are running away from us than the close by galaxies. Which means if you have a galaxy that is 100 megaparsecs away, it's only running away from you at maybe 100 kilometers per second. But if you have a galaxy that's 500 megaparsecs away, it's running away from you at like 3,000 kilometers per second. So the farther away you get, the faster it's going away. And the slope of that line is what's known as the Hubble constant. And we have a pretty good idea of this slope, of this graph, because we have actual data from supernovas and Cepheids for tens of thousands of galaxies. And so we have a lot of data points, and we can fit a very well-defined best fit line through all those data points. When we find a new galaxy that does not have a supernova in it, or it's too far away to see an individual Cepheid variable star, all we need to do is measure its redshift. When we measure its redshift, we know how fast it's moving away from us, because those spectral lines will be redshifted a certain amount. We can calculate its speed, its recession velocity as it's known. Let's say we find a new galaxy and it fits right here on this line because it is moving away from us at 2,000 kilometers per second. Well, that galaxy is 300 megaparsecs away. Did we see a supernova in the galaxy? No. But because we have this graph, this slope right here is going to tell us how far away that galaxy is. Let's say the slope was different and the slope went kind of like this. Well then, if this is the slope, then a recession velocity of 2,000 would give us a distance of maybe 600 megaparsecs. So this slope is very important to get pretty accurately. Hubble thought that this slope was about 500. Right now we believe it's about between 65 and 75. So he was pretty wrong. He had the right idea, but he was off by an order of 10, by a magnitude of 10. We have refined, we've gotten better data, and we have narrowed that value down much better than he was able to. Based on this slope, which tells us how fast things are moving away from us, if you run that backwards, you can tell when everything was all in the same place. You can tell when the Big Bang happened. So this slope, getting this correct, is going to tell us the age of the universe. And right now, there's two schools of thought. The first one is that the Hubble constant needs to be around 50 kilometers per second for each megaparsec away from Earth you are. And that is reached by looking at the oldest stars. The oldest stars are like the Methuselah star, which is a hard name to say. Based on how old that star is, we went back in time and figured out when the universe would have had to begin. The other one, though, is taking a look at this data from these receding galaxies. And then we get a constant between like 67 and 75. The problem with that, though, there seems to be a mismatch between how old the universe is and how old the oldest stars are. There seems to be stars that are older than the age of the universe. Here is a good video going over that. If you talk to most astronomers, though, they are going to say that the Hubble constant is about 67 to 75 kilometers per second for every megaparsec away from planet Earth you go. You'll notice, depending on which measurement you look at, it's anywhere between like 67 and 75. There's a bunch of error bars because we're talking about huge distances here. If we can nail down exactly what the Hubble constant is, well, we can run that backwards and we can figure out the age of the universe, we can figure out the size of the universe, we can figure out the shape of the universe, as well as what is going to happen to the universe in the future. So figuring out the Hubble constant is very important for astronomers and can give a lot of information. One possible solution between those two schools of thought that takes into consideration the oldest stars is that maybe this expansion hasn't always been going at the same speed. Maybe it's speeded up recently. It started out slow so you could get these old stars, and then now when we're looking, it seems to be going much faster. So if the universe's expansion has sped up, there has to be a reason. Einstein actually came up with it. When he came up with his theory of relativity, the equation didn't quite work right. And in order to balance the equation, he came up with what is known as the cosmological constant. It's this anti-gravity that's pushing out against the universe. Because if it's not there, then the gravity of all the galaxies and planets and stars should cause the universe to shrink. But we don't see that. So he came up with this imaginary force he called the cosmological constant that's pushing out against gravity. Later in his life, he kind of admitted that he made that up. That he doesn't know what it is. And he called that the biggest blunder of his life, is making up this random outwards pushing force. Turns out that dark energy could possibly be an outward anti-gravity pushing force. Decades after Einstein died, we discovered dark energy. Dark energy is an outward pushing force. It turns out that Einstein was correct. There is an outward pushing force counteracting gravity. So what Einstein thought was his biggest mistake, his biggest blunder as he called it, turns out he was predicting dark energy decades before anybody else. So even his mistakes make him smarter than any other scientist.
Let me tell you how smart Einstein was. In one of his equations, he put in a term that he later regretted putting in, and he called it his greatest blunder. This is a term that he looked at his equations, and his equations showed that the universe had to be either expanding or collapsing.
Right.
Now, no one had any idea that the universe, which is everything, would be doing anything.
Yeah, it's just there.
It's just there,
Right.
right? So he says, this can't be right. Let me put in this term. It's a legitimate mathematical term, but physically, what the hell are you doing, Albert? And he says this term will help stabilize it from collapse. Okay, and it's a pressure force to push outward, and that'll stabilize it. Later on, just a couple of years later, Hubble, the man after whom the telescope was named,
Telescope, the man,
discovered that in fact the universe was expanding, and he didn't need the term because he could have predicted that the universe should either be expanding or contracting, but he didn't. He put in this term. He said it's his biggest blunder. Now, you know what Einstein's actual biggest blunder is? Saying that that was his biggest blunder.
Yeah.
Because in fact, in 1998, we discovered a pressure in the universe pressing against gravity that is exactly the term that he put in.
it wound up being what he said.
His
not
biggest
a blunder at all.
blunder is thinking he made a blunder.
Uh-huh.
That's how smart he is. That's badass smart.
So right now, dark energy is actually kind of acting as an anti-gravity and pushing out, causing everything in our universe to fly away from each other faster and faster and faster each and every day. So not only is the universe expanding, but that expansion is speeding up. So right now the universe is expanding, but tomorrow it will be expanding faster. And the day after that, it will be expanding even faster. Dark energy, we'll get there later in the year, but short answer is we have no freaking clue. It is a huge mystery. We don't know. So I don't have an answer for you. If we ever figure out that answer, it's going to be one of the biggest discoveries in all of science, in all of history.
So when you put all that together, what do you get? Well, so we've got lots of distant galaxies. We know how far they are away. We know how fast they're receding. What we find is something called the Hubble Law. And it's basically very simple. It says that the further a galaxy is away, the faster it's flying away from us. Now, how are we to interpret that? I mean, you might naively say, well, does that mean we're somehow at the centre of the universe and everything's flying away? Well, no, actually. If you think a little bit more, if you think, for example, about baking bread, if you get a lump of dough and put raisins in it and stick it in the oven, then the bread expands. So all the raisins move away from every other raisin. If you were sat on one raisin, what you would see is the Hubble Law, exactly the Hubble Law. You'd see the ones close to you moving away more slowly, the ones further away moving away quicker, because the bread is all stretching. All of space is stretching at a constant rate. So you get this fascinating law, which is exactly what we observe. And I wanted to give you the number, because it's a very interesting number. I gave a lecture. I don't know if any of you know The Hitchhiker's Guide to the Galaxy. Do any of you know that? Douglas Adams? Yeah, you do. Brilliant. Very good. If you don't know it, you should read it. It's a wonderful, funny, hilarious book. In Hitchhiker's Guide to the Galaxy, it's a very famous number, which is the answer to life, to the universe and everything, and it is the number 42. It's been famous for years. Everyone who knows Douglas Adams knows the number. It does actually turn out, remarkably, the Hubble constant can be written like this: 42 miles per second per 3 million light years. What does that mean? It means that for every 3 million light years you go away from the Earth, then things, if you go 3 million light years from Earth, so let's just step 3 million light years away, then on average things will be moving away at 42 miles a second. It's pretty slow, actually. If you go 6 million light years, things will be moving away at 84 miles a second, and so on. So every 3 million light year step you take, you add another 42 miles per second to the recession velocity of things.
Everything is expanding away from everything else, which means that no matter where you are, it seems as though things are moving away from you. So if you are in Galaxy 3, this close by one is moving away from you at 7,000 kilometers per second, and Galaxy 5 is at 14,000. But let's say you are living in Galaxy 2. Well, Galaxy 3 is moving at 7,000 kilometers per second, Galaxy 4 is at 14, and Galaxy 5 is at 21,000. So the farther away from Galaxy 2 you get, the faster these galaxies are going. But it also seems as though this one is moving away from you the same speed as Galaxy 3. So you can pick any galaxy, and all the other galaxies are going to be moving away from it, and the farther away you get from the galaxy that you chose, the faster they're going to be going. So it seems as though any galaxy in the universe has everything else expanding away from it. So it seems as though any galaxy in the universe could be the center of that expansion. Using the words redshift, expansion, recession velocity, I would like you guys to answer the question of the day. Now you get to practice.
The quantum vibrations of molecules